So now we're going to start talking about the equilibrium constant. And before we do, I need to get my mouse back just a minute. There it is. I'm going to show you a couple ways you can see this. Capital K is considered the equilibrium constant, but that K can be modified with a subscript. So K sub C would be the equilibrium constant. KEQ, where EQ is standing for equilibrium, also represents the equilibrium constant. Later on, you are going to see Ka, which will be an equilibrium constant for acids, Kb, an equilibrium constant for bases, KSP, which I think we maybe mentioned briefly. This is a solubility product constant. So all of these are modifiers of the K, which is the equilibrium constant. For what we're going to be talking about right now, Kc and Keq are what you're going to see more in this chapter. You will also see K sub P, which is the equilibrium constant for pressures. So now what I want to show you how to do is how we write the equilibrium constant. So let me... All right, so let's say we have a chemical equation where we have reactant A, reactant B, reactant C, product C, and product D. And each of these has a coefficient. Let's make A's little a. Let's make B's little b. We'll make C's little c. And we'll make D's little d. And so these are representing coefficients in the balanced equation. So if I want to write the equilibrium constant, and I can be doing K sub C or KEQ, I'm just going to do KEQ. What I want to do is I want to take the concentration, so I'm going to use brackets, of the products, so that would be C and D, and I'm going to raise them to the power of their coefficient. So D will be raised to the D power, C will be raised to the C power, and then that will be over the concentration of our reactants raised to the power of their coefficients. Now there's other rules for doing this, which I'll share with you in a minute, but that's basically how we would write what we call an equilibrium expression, and that's the way you're going to see it on the AP exam. So if you are asked to write an equilibrium expression, which you will be, that's typically the first or second question in an equilibrium problem. They'll say, write the equilibrium expression for, and then they'll give you a reaction. This is exactly what you're going to do. Now, the trick with this is if these are gases, we know that gases can exert pressures. And so you might be asked to write the equilibrium constant for pressures, which would be K sub P. This looks a little bit different. You can't use the concentration brackets with pressures because pressure and concentration are not the same thing. So what we do instead is we use a P for pressure, and then we modify that. Let me get this set up so that it's easier for me to change colors. By doing a subscript with the product, we still raise it to its power. So we'll have the pressure of D raised to the power D over the pressures of our gaseous reactants. So the pressure of reactant A raised to the A power times the pressure of reactant B raised to the B power. And this is still an equilibrium expression, but this is for pressures. So that's one of the things that you need to pay attention to as we do these. So now let's do it with real reactions, real compounds and elements. But before we do that, we want to go through a couple rules for writing equilibrium expressions. And there aren't many. There's just a couple. Rule number one is that we do not, I'm going to underline that a lot, include solids and pure liquids in the equilibrium expression. And the reason we do not include them is because they do not exert a measurable pressure, nor do they have a concentration. So you don't want to include either of those. The second rule is that we do include gases because they will have a pressure and they can have a concentration. And we also include ions or anything that's in aqueous solution. So we're going to know that when we look at the reaction, because they will give us state symbols, and you are going to see an AQ following anything that is in solution, whether it's in ions form or not, ionic form or not, and then anything that's a gas. But you're not going to include solids and pure liquids. So now let's go to some actual examples. So I've got two here. I've got one in which I've got 2 moles of ammonia, gaseous state, going to 1 mole of nitrogen gas and 3 moles of hydrogen gas. So what I want to do for this one is I'm going to do both. I'm going to write the equilibrium expression for using concentrations. So I want to do concentration of my products, which would be nitrogen right here, times my other product, which is hydrogen. But you notice that hydrogen has a coefficient of 3, so I want to be sure to include that coefficient of 3. And then that is going to be divided by the coefficient of, it's going to be divided by the concentration of our reactant raised to its coefficient power. All of these are included because they're all gases. And then this is our equilibrium expression for the reaction given above. Now I want to do the same thing for pressures. So this is going to be the equilibrium constant for pressures. So it's going to be K sub P. This time I'm going to use P for pressure of nitrogen. I'm not giving that a coefficient because this has a coefficient, or I'm not giving this a power because this has a coefficient of 1, and so 1 is just the itself, times the pressure of hydrogen raised to the 3rd power because it has a coefficient of 3, divided by ammonia gas, which will have a pressure, and then I need to raise that to the 2nd power. Whoops, it didn't change color, sorry, because it has a coefficient of 2. So this here is my equilibrium expression, or for that same reaction, but this time I'm using pressures. So let me do this one, because this one's a little trickier. I'm going to do, oh, let's change color just because I feel like it. I'm going to do the equilibrium constant for concentrations. So I want to do products, and I include gases or anything that's in aqueous solution. So yes, I'm going to include sulfur dioxide. So sulfur dioxide in brackets, not raising it to a power because it has a coefficient of 1. I'm going to put that over concentration of reactants. I will include oxygen because it's a gas. I'm not giving it a coefficient because I'm not raising it to a power because it has a coefficient of 1. And then I am not going to include sulfur because it's a solid, and solids are not included in the equilibrium expression. So this is my equilibrium expression for that second reaction. Okay, now one of the other things I want to mention is that typically the reactions that you are going to be given will have a temperature associated with them. And often it'll just be 298 Kelvin, which is 25 degrees Celsius, so standard state. The reason for this is because equilibrium constants are a particular number at a certain temperature. And as temperatures change, then the value of this equilibrium constant will change. If you think about it, we're talking about concentrations or we're talking about pressures, both of which will be influenced by changes in temperature. Concentrations are really moles per unit volume, and volume is affected by changes in temperature. So if volume changes, then naturally our equilibrium constant is going to change. Same thing with pressures. Temperature affects pressure. So if our pressures change, then our equilibrium constant for pressures will change as well. So you'll notice that there's temperatures that are always given, and that matters because pressures and concentrations can change with temperatures. So last thing we need to do is talk about, whoops, I went too far, sorry, what equilibrium constants tell us. Why are they a big deal? Why are they important? Why do they matter? So what I've written here is kind of a lazy way of writing this, but I'm doing it because I want you to think about the relationship between the concentration of the products divided by the concentration of the reactants. So we're going to get a numerical value for our equilibrium constants, and I don't think that purple was a good color, so I'm picking a different one. So we can have equilibrium constants that are going to be large, and we define large as being greater than 1. We can have equilibrium constants which are less than 1, and we will call that small. I don't like the little dot there, so I'm going to get rid of it. And we can less frequently have an equilibrium constant which is equal to 1. And that's much more rare than the other two. So if we think about what these mean, if we have an equilibrium constant that's larger than 1, that means that, let's say this number is big. So if you think about the relationship between concentration of products and reactants, what has to be true is that your concentration of products has to be greater than your concentration of reactants. And so what we say in this situation is that the reaction is product favored, or the equilibrium lies to the right. So product favored or the equilibrium lies to the right. So if you think about the demonstrations that we did in class, you can think about when these situations were occurring and when something was product favored. This is what goes on when you're talking about like a strong acid or a strong base. Everything is toward the product side. If you have a, let's change this. Let's say, okay, now our equilibrium constant is small. So it's teeny tiny. In order for that to be true, the amount of reactants has to be much greater than the amount of products. And so we call that reactant favored because we have more reactants. And we say that the equilibrium lies to the left. So reactant favored, or the equilibrium lies to the left, which means we have more reactants. That would be the situation that we have with weak acids and weak bases. And then in this rare situation where the equilibrium constant is equal to 1, so this number here would be 1, that would mean that our concentration of products and our concentration of reactants would be equal. So we would say that would be equal amount, really it would be equal concentrations. I'm going to use the concentration brackets of reactants and products. And so if we're talking about to which side the equilibrium lies, we would say equilibrium lies in the middle. And this is not as common as the other two situations where you've got an equilibrium constant that's greater than 1 or an equilibrium constant that is less than 1.